Okay, this will be section 1.2 from the ZIL textbook. We're still in chapter 1 in the Shams outline. We're doing initial value problems. So think back to really the end of Calc 1 and all through Calc 2. Say you were trying to solve this indefinite integral. That, for fun, let's call the inside the integrand f of x, 3x squared. Remember, the whole point of an antiderivative is we're looking for some function capital F whose derivative is little f, the inside. You can do that in your head. You know the antiderivative there is x cubed plus c. Notice we have an infinite number of antiderivatives. Remember, we have this whole family of antiderivatives, all of which satisfy being the antiderivative of this guy. Because if we take the derivative, we'll get 3x squared plus derivative of a constant is 0. So there are an infinite number of solutions. What if we want one of those solutions in particular? What if we say we want to ensure that f of 0 was 5? So we just plug in a 0 for x, and get 0 squared plus c. That's supposed to equal 5. So c must be 5. We've just solved an initial value problem. So instead of having an infinite number of solutions, we have one of them in particular. We call that a particular solution. So this function here was the general solution to this antiderivative. This function here is one of the particular solutions. And I could have given it a new name instead of calling it f. That doesn't really matter here. By the way, you may not realize it, we have just solved our first differential equation. This really was a differential equation. I'm looking for some function whose derivative is 3x squared. So I'm really solving dy dx is 3x squared. Anytime we're doing an antiderivative, we're solving a very simple ordinary differential equation. And we solved that subject to this initial value condition. We wanted y when x equals 0 to be 5. I know this notation looks different because we're not used to this, but y is a function of x here, so this says y of 0 is 5. And that solution to this initial value problem is y equals x cubed plus 5. In general, if you have an nth order ODE, you'll need n initial value conditions to get a particular solution. You'll need one for the original function and one for each derivative up to n minus 1. So if we had a fifth order ODE, we would need 5 initial value conditions. Y of 0, y prime of 0, double prime, triple prime, and fourth derivative all at 0. Okay, here's another example, a little more complicated. Suppose somebody tells us that this function here is a 2-parameter family of solutions to this ODE. So here our independent variable is t, our dependent variable is x. This is a second order linear differential equation. We're going to solve the initial value problem subject to these two initial conditions. We had a second order DE, so we need two conditions, x at 0 and x prime at 0. Okay. Notice, by the way, we have two unknowns. We had C1 and C2. Those would be our two, really, those are constants of integration. That's where those come from. Just like up here, when we integrated, we got a constant of integration. Here, to solve this, we'd have to integrate twice, so we get two constants of integration. So in general here, because we have two unknowns, we would have a system of linear equations. This one just turns out to be pretty simple. By the way, this causes trouble a lot of times when people are working these. We could verify that this function is a solution to the ODE, but it's not necessary. Nobody asked us to do that. I'm just trying to find C1 and C2. I'm never going to use this thing right here at all. I didn't even have to give you that. I could have erased this and you wouldn't even know the difference. We're trying to find C1 and C2. So we're going to plug this value into the original. We're going to replace t, that's my t, with 0, and x with -1. Cosine of 0 was 1, sine of 0 is 0, so this whole term disappears. We got lucky here. We just, instead of getting a system of equations, we get immediately C1 equals -1. Now we play the same game with the second condition. We need x prime at 0 to be 8. So again, don't use the ODE, go to x. We know the solution. Take the derivative, plug in 0, and set it equal to 8. So here's the derivative of our solution. We plug in 0, sine of 0 was 0, cosine of 0 was 1. This term drops out. I know we already know C1. I could have just put a -1 there because we already know C1. It doesn't matter here because it cancels out anyways. Cosine of 0 was 1, so we get C2 equals 8. So then we know C1 and C2. The particular solution to this initial value problem is this function here. No arbitrary constants in there anymore.